Thank you very much for the kind introduction, and thank you very much for having me here as one of the few presenters from industrial corporations here at this conference. Very insightful presentations we have seen here in this conference, and now a little bit more into the double laser processing and the possibilities of using this double laser processing to obtain functional graded materials at the end. So this will be the overall topic of my presentation. And of course, because I'm from a company, I will show you a short introduction about the company Rostbach. The classic business field of Rostbach is in the area of open die forging and ring rolling, with part weights up to 4.5 tons out of 400 different alloys. A process that is a lot different to the metal additive manufacturing process. The company has 200 employees, is family owned in 5th generation, and in 2014 I had the possibility at this company to establish the metal additive manufacturing division called Rostbach Engineering. And since then we grew a lot. We now have 4 LPBF systems and 50 people working there in all kinds of areas. And what makes it special on the market, in our opinion, is that we have a pretty holistic process chain and also can do our own special metal powder production with a small-scale atomizer from Blue Power or Nickel, with around about 4 liter crucible volume, so we can produce up to 50 kilograms special metal powders there. We have already qualified 40 different materials with our in-house process chain in pretty short lead times, each of them. And if any of you has, for future research work, need for special metal powders, just drop me a message and I will care about this and send you an offer back. And now back to the presenting topic. I will talk today about the area of LPBF tool seals. And as all of you may know, the carbon addition to steel has some benefits when it comes to the mechanical properties, but also of course some disadvantages when it comes to the processability. We can clearly see on the picture on the right side that there are some pretty big cracks on a leaderitic steel we tested in-house. And it has a carbon content of around about 1.3 weight%. And that's why, especially on industrial applications, most of the companies are using the Maraging steels for LPBF processing. The concept is there that you have a soft nickel martensite, and it is developed strong intermetallic precipitations during aging, during heat treatment, and a well-known material in this class is the FeNiCoMoVTiAl, which can go up to a hardness of around about 660 Wicas. But the material in my study is not the FeNiCoMoVTiAl. We have qualified new material based on the FeNiCo350. We call it Specialis. And it has also a sufficient vanadium addition to it. And what we have seen in initial tests is that we get superior mechanical properties, especially compared to the FeNiCo300 alloy. You can see here, go front a little bit so they can see it by myself. Here the S-build properties, and S-build hardness is typically for the Maraging tool steel, so that's around about 340 Wicas. And after the aging treatment, you can go up to 725 Wicas hardness. And after solution annealing, quenching, and aging, we can go up even above 800 Wicas hardness. What we think is pretty special currently in the market to have such a hard material that you can print or you can process on LPBF systems and optimize regarding the needs during the heat treatment. So, what is the basic principle of my study for using for going towards the functional graded linear structure is that it is the aim to locally modify the thermal gradients during the LPBF processing, and our approach was to use 2 lasers of our SLM280 system, both lasers in a synced mode, so that the second laser follows the first one and influences locally the thermal gradients and the cooling rates, and by this affecting the in situ heat treatment, and so leading to special mechanical properties. So we had to modify our SLM system for that. We had to modify hardware, we had to modify software to make this even possible, and especially to sync the 2 ScanLab control cards for a synced clock rate. So we have a synchronized laser control, especially in the small overlapping scan field zones you can see here in the build chamber. And of course, it's also important to have a look at the dual laser exposure strategy that we derive from the different constraints we have in this process. We had the possibility to use the standard hill processor systems by, for example, Magix, to make the exposure strategy and slicing the parts. So we had to use a CSV table file and make more or less a G-code programming of each scanning and jumping vector. You can see on the right the principle of that. The main constraint was, of course, the melting fuse produced by the 2 laser beams. So they shouldn't interfere the other laser, and this would definitely lead to some problems in the process. So we tried to, by turning in an angle of around about 45 degrees, the specimen, that they won't interfere too much each other, and of course what is important is the beam offset between the 2 lasers that will lead to special influences. So next slide. Yeah, you can see the experimental design. I had a look at 3 different melting modes. The classical single laser mode, you all may know, we have the melting zone, the solidification zone, and the heat affected zone within our melting track. And the new melting mode was melting mode B. You can see how the laser 2 will be added after a certain distance to the melting track, and we met just a fraction of the previously melted volume, and by that extend the zone of in situ heat treatment for a small area of the already melted track. And this should help to locally modify thermal gradients and cooling rates. And for also as reference, we use the remelting mode. You all may know that means that we have a longer time lag between the 2 laser systems melting and remelting a certain area of the part. And you can see the different parameters we had a look at here. All single laser parameters was the same. That means all parameters for laser 1 were the same, and we just changed the parameters for laser 2, 125 watts and 200 watts. And for 200 watts even we used the defocused parameter to not being so having a too deep melt pool, more or less a wider melt pool here, and yeah, tried to have a look on different melting laser offsets. And as we can look at the initial results here, what was the first benefit we see here? We have a very high material density. We could obtain for all tested parameter sets more than 99.7% material density. And the main difference you can see here between the different laser parameters. We have here single laser, we have here dual laser with 125 watt, and here the dual laser with 200 watt and defocus. Both dual laser parameters with a 4 millimeter distance between the 2 lasers. You can see here, especially on the first layer, Here you have the normal melt tracks from the one laser. Here you have the melt pools from the first laser, and within a small melt pool of the second laser beam that followed the first one and remelted a certain area. And here on the dual laser mode with 200 watts, you can see the wide melt pools by the defocused 200 watt laser, and also influence a certain area on the surface layer. But when you look deeper into the part material, there was no significant influence on the melt pool structure, and the melt pools were generated on all modes mostly by the first laser and by the standard processing parameters. But as we look at the mechanical properties coming from the different parameter sets, you can see here in this figure, you can see that the single laser mode is around about 440 Vickers hardness as a result, and we could increase the hardness, especially for the dual laser strategy with 200 watts significantly. You can see here, and during all the tested offsets between the two lasers, and we could decrease the hardness by using a remelting parameter set based on the 125 watts. And this was the first principle. We thought, okay, we have it tested on single specimen with single parameters. Let's test it in a part that has multiple parameters within. So here you can see 1/3 of the part was melted by the dual laser mode with 200 watts, 1/3 was melted by the single laser mode, and 1/3 was melted by the remelting mode. And you can see there's, let's say, something like a graph, like a function of the hardness evolving over the building, and this leads to the possibility of functional grading the material regarding to your needs based on the parameters, but with the advantage that we don't affect the melt pool sizes that lead to defects within the structure and could lead to failure at the end when there comes a load on the part. So we obtained a more or less consistent melt pool structure all over the part, but with varying hardness values, and especially if I switch there, for example, the dual laser and the single laser mode. In the next slide, you can see how the hardness level changes between the two strategies when manufacturing the part. And as the Matteo Saita today told us in his inspiring keynote, in our opinion, this is the next level of additive manufacturing. If you have the ability of not just modifying the geometry of the additive manufacturing part, also have the ability of modifying locally the mechanical properties of the part and leverage full advantages of additive manufacturing in future for industrial needs. And as I'm from a company, please excuse the final announcement I have to make here in this presentation. We all know that doing such studies leads to a big effort. We have to do a lot of experiments, a lot of validation work is needed. And what we thought of is, let's transfer already existing knowledge to industrial applications by establishing our AAMS platform. That means you can trade LPBF parameter sets and corresponding material data for all kinds of systems and all kinds of materials in the market. And this, in my opinion, will help in future that the industrial service providers can also use the full potential without investing too much in the big experiments and a lot of work that is needed to really validate and qualify new parameter set and new material. So we will start this AAMS platform with the marketplace in November during ForNext. And if you have any questions about this, just get in touch with me or go to edimap.com. And yes, thank you very much. I'm looking forward to your questions.